Thank you very much. Welcome to the Lesush. So Stefano already introduced me, but I would like to spend really less than a minute to introduce my lab, called the Center for Nanoscience. Nanotechnology was founded in 2018 in the fusion from two previous labs of the CNRS. We are located on the Saclo Plateau, close to École Polytechnique and IPVF. It's a couple of blocks away. And the lab is composed essentially by a little bit more than 400 people, 4 departments: photonics, nanoelectronics, material, and microsystem and nanobiofluidics. We do have a relatively big clean room facility of almost 3,000 square meters, and there's activity ranging from fundamental physics, epitaxial growth, 3.5, and other things. So today I would like to shortly introduce you to the 3.5 photovoltaics. I will try to keep it short because we don't have much time. So we'll start to introduce the 3.5 semiconductor compounds and why they are very interesting, not only for solar cells but also for opto-electronic devices. And I'll show you how this, at least for photovoltaics, these solar cells were evolved from a space application down to Earth. And I will talk a little bit about the problem. It's a very hot topic now in the PV community of a tandem on silicon. 3.5 could be one of the options for the top cell. And if I have time, hopefully I will talk a little bit about the problem of 3.5. I would argue that it's not the efficiency, the problem here, but it's the really high cost of these solar cells, mainly coming from the expensive substrate. So 3.5 semiconductor compounds are essentially alloy of elements from the third column of the periodic table and the fifth column of the periodic table. So if you start with silicon, you can get, again, these 8 electrons alloying, for example, on gallium arsenide and arsenic. And starting from silicon 1.1, you have a material, that gallium arsenide, with a slightly higher band gap. You can actually go further and alloy, for example, cadmium with tellurium, and you get cadmium telluride, and you will have a slightly higher band gap. But this is another story. What you can do also is to alloy different materials, for example, aluminum and phosphorus, and you have an even higher band gap, or you go in the other way around, indium and antimonide, and you get a very small band gap. And of course, you can start to change the alloy, and you see you have immediately a lot of different materials with a lot of different band gap. And of course, you can extend the thing and try to alloy 3 or 4 different materials, and it's getting really messy now. So what we normally do is to plot this kind of graph. Here you have on the y-axis the energy band gap of the alloy, and on the x-axis the lattice constants of the crystal you are growing. For example, if you look at the gallium arsenide, it's very fortunate that whenever you are alloying with aluminum, you do not change basically the lattice constant of this crystal. And so it's a good platform to create heterojunctions or heterostructures in general. And this is one of the first couple of materials that were used for example, for lasers. But of course, you can also alloy gallium arsenide with indium phosphide, and whenever you achieve more or less 50-50% of indium and phosphorus, of gallium and indium, you will end up again to have a crystal that is lattice match with the gallium arsenide. So I insist very much on this lattice parameter, because whenever you grow crystal, and all of these crystals are normally made by the epitaxial growth, you need a substrate on which you want to grow them. For example, gallium is not that far from germanium, and silicon is around here, so it will be lattice match more or less with gallium phosphide. Although with gallium phosphide there's not much to do, but we have a lot to do with these other materials here. I'll come back later on this point. So just a note on the fact there is a particular class of material called nitrides, where the fifth element will be nitrogen this time. And in this case, you can even scan a very, very large range of band gaps. So here is I highlight the previous graph here. So you see it's very, very large. The problem with these nitrides is that we do not have a lattice match substrate on which we can grow them. At the moment we are using sapphire, although it's not really very much close, the lattice constant, and it's clearly expensive, so the quality of these materials are still not at the same level of the more conventional 3.5. So one of the very interesting features of this material is that you can have and control energy band offsetting between two different materials, let's say material 1 and 2. And this band alignment can have a very different configuration. Most of the time we use this configuration here, the type 1, the straddle. For example, is the case for gallium arsenide and aluminium gallium arsenide. And of course you can measure, and it's not trivial at all, or predicted experimental, theoretically, the band alignment of different materials to respect to the others. So this, the possibility to create heterostructure, I want to stress a point that sometimes is forgotten by students, is that whenever you dope your semiconductor, you do not change the band offset in between, for example, the conduction band of the first material, the conduction band of the second material, at least not at the interface. You preserve it here. Of course, you will align the two in the bike, so don't forget this. So with this class of material, it's really the best way to implement this double heterostructure, for example, that was used for and is still used for lasers, but also in the solar cell when you have the absorber and then two selective contact, and you can have this barrier, I was already mentioned by Hoover, where you can repel minority carrier and collect on the other side the majority carrier. So why these materials are very interesting? From the electrical viewpoint, they feature extremely high carrier mobility. This is the plot for mobility charges for electron and hole for different kind of 3.5 semiconductor materials versus the lattice constant. You see also here you have the silicon and germanium. They are few order of magnitudes lower. They also have a direct band gap, although silicon has an indirect band gap, and with a very relatively high optical absorption coefficient. Here, for example, you have the gallium arsenide is not a step function, but it's not that far, let's say. The other interesting point that is very useful for solar cell or LED is the fact that they feature extremely high internal quantum efficiency. The internal quantum efficiency is the ratio between the photogenerated carrier and the photons that are actually absorbed inside the solar cell. So here you have a plot from a nice paper from Martin Green, where he plotted the three curves are the Shockley-Queisser limit in the case of 100% external radiative efficiency in this case. So in this case, it's the ratio between the impinging photons and the photogenerated carrier and the impinging photons. So you have to absorb them first. In the case of 100% external radiative efficiency, and whenever your material has a lower external radiative efficiency, you can expect a degraded Shockley-Queisser limit. This was, if I remember well, the fourth hypothesis in the list of 5 of Hoover, when you saw that by introducing other recombination mechanisms such as Auger or surface recombination or bulk recombination, then you really reduce the VOC. And another way to see this is with these plots, always from the same paper, where you have the energy conversion efficiency for experimental solar cells with different technology versus the external relative efficiency. And you see how, for example, the gallium arsenide stands there alone because it features a very high efficiency. This is due to the fact that for such a material, the difference in between the band gap and the actual VOC or splitting of the quasi-Lerner Fermi level is very reduced for gallium arsenide. This is something, again, that Uwe showed you before. So yeah, as I was mentioning before, 3.5 solar cell are, let's say, best in class for single junction with the state-of-art owned by Alta Device at 29.1% here, but also for multi-junction here. And they are also used, as mentioned by Uwe, for a certain number of new concepts that you will see on Friday, hot carrier solar cell, intermediate band, and so on and so forth. So yeah, this is a zoom of this NRL plot. So everything started, I was mentioning before, in space. And in space, the condition, as already mentioned by Uwe, are slightly different. We do not have atmosphere. We have a little bit higher intensity of the sun radiation. The black body is slightly It's not filtered by the atmosphere, slightly richer in the blue part of the spectrum. But the big deal here is that you have high energy particles, electrons and protons that are ionized, produced by sun wind, and then trapped by the magnetic field of Earth, and then create this Van Allen bed that basically these high energy particles degrade your solar cell. Essentially, you have some atomic displacement inside the semiconductor. And as you already know, or you will learn, a solar cell will work until the diffusion length of the minority carrier is longer than the thickness of the cell. So when this is not anymore the case, because you introduce a lot of defects in your bulk material, then the solar cells stop to work. So that's why thin cell, in particular 3.5, they are direct bandgap material, works well, and actually it works better than silicon. The other point where solar cell based on 3.5 exceed performances as compared to silicon is the fact that they can support better temperature variation, and in space you can have very, very harsh temperature variation ranging from minus 100 degrees or plus 140 degrees on Mercury on Venus or something like that. So this is why I will try to short a little bit this part, because it's just an historical thing. In the 60s, they started to observe this better tolerance to radiation of gallium, for example, or gallium arsenide solar cell as compared to silicon. And since then, it really started to create this PV of 3.5. Main point was to the first heterojunction, where they used this P-type window layer made of algas with an N-type base. So this P-type contact is conventionally called window layer. At that moment, the fabrication process was based on liquid epitaxy. I'll come back a little bit on the different technique of epitaxial grow we use today. And the improvement started to get better efficiency for 3.5 solar cells compared to silicon. And till nowadays, when we normally use 3-junction solar cell, normally made by MOCVD, again I will come back on these technologies, grown on germanium, because germanium is cheaper than gallium arsenide and is more mechanically robust. Yeah, it's interesting to know, just a note very quickly, that indium phosphide based materials are in general way more resilient to degradation induced by high energy particles. And here, for example, you have the efficient degradation versus the fluence of this high electrons beam for an indium phosphide cells, and you can see it's pretty flat. For indium gallium phosphide, and then you have gallium arsenide, and then you have silicon with two different thickness. The worst is the thicker silicon solar cell. Although it didn't make through space, mainly because at that moment we were lacking a good enough, let's say, a window layer. Now we have aluminum arsenide and timonide that works well, also for example, for quantum cascade laser. But the big deal here is that, big problem here is that indium phosphide is extremely expensive. Maybe it's like 20 times more expensive than silicon. And we do not have a cheap substrate that is lattice match with indium phosphide, being silicon 8% smaller and germanium 4% smaller. So we didn't make it through. So here, I'm just one slide on the epitaxial grow method we use for 3.5 materials. So at the beginning, as I already mentioned, a lot of devices were made by liquid phase epitaxy. This is a solution-based epitaxial grow of crystals. The solution in this case is a melted metal. For example, for gallium arsenide would be melted gallium. And it's performed in atmosphere pressure with some high purity hydrogen. And it gives you really, really excellent crystal or crystalline quality, stoichiometry, and interfaces. The big problem with this technique is that it's very, very difficult to control the thickness of the layer you are growing because of the very high surface energy of this liquid metal. And nowadays, as far as I know, it's mainly used for the production of LED, and is also used from some group, including us, for example, to grow catalyzed, gallium catalyzed, in this case gallium arsenide nanowires on top of silicon. I'll say something very shortly afterwards on this technology. The other main technique are molecular beam epitaxy and metal-organic chemical vapor deposition, otherwise called MOVPE. So in this case, it's a vapor solid technique. You're essentially evaporating atoms in vacuum, and they will condensate on your substrate, atoms by atoms. The problem, the condition to do this epitaxial grow is that you really need to have a very high, ultra high vacuum in the range of 10 to the minus 10 torr. To give you some order of magnitudes, if you take your sample in your reactor, for example, at an atmosphere, on a residual pressure of 10 to the minus 6, and of course, this residual pressure is induced by atoms, residual atoms that are in the reactor, like carbon, hydrogen, also some water. Well, if you assume that all the atoms that impinge by chance on the surface of the substrate will stick on it, it will take just 1 second to create a monolayer, a monatomic layer of material. So 1 second, 10 to the minus 6. So it's clear that you need a very low pressure, a few orders of magnitudes lower pressure, if you want to make any experiment of surface science, and Philip will probably mention this, or if you want to grow a good crystal in vacuum. So that's why we need this very low pressure. But the good thing about molecular beam epitaxy is that you can grow at very low rates. You can control precisely the thickness of the layer we are growing at the monolayer level, and so we can create some quantum-based device, and so you can have quantum confinement, quantum hole, and so on and so forth. So at the moment, it's mainly used for proof of concept, at least in photovoltaics. It's not the case, for example, for lasers. It's still used for lasers. And I believe that in photovoltaics might be used to grow some diluted nitride to replace one of the 3 cells in the current 3-junction cell we use for space. But you have a reference, I won't talk about this. So the third method is MOCVD. This time it's a chemical reaction of a precursor you have in the chamber. For the third, the element 3 will be a metal organic, and from the element 5 will be anhydrides. It's normally carried out at relatively low pressure or even atmospheric pressure, again in pure hydrogen. And as for the MB, you can control very precisely the thickness and the interface of your devices. And is actually currently used for the choice of for commercial 3.5 device. Also because the advantages compared to MB is that you can go at very high, also at very high deposition rate. And I think Fraunhofer a couple of years ago shown that you can actually achieve range in something like 100 micrometers per hour, which is really fast. So coming back to the gallium arsenide solar cell structure, gallium arsenide, the big deal, it's a big deal for any solar cell, but in particular for gallium arsenide is the surface recombination. And you can see it here. You have the surface recombination velocity for 3 different materials, but we will focus only on silicon and gallium arsenide. You see that, sorry, already if you take silicon with some native oxide or gallium arsenide with native oxide, you have a very different recombination velocity, lower for the silicon. And for the silicon, actually, if you use a thermal oxide and use some tricks, some annealing, for example, it can be extremely low. For gallium arsenide, the best we can do, as far as I know, is to use, again, aluminum gallium arsenide. So you have this type 1 heterostructure, so you're preventing the carrier to recombine. You basically prevent to have a pinning of the quasi-Fermi level in the middle of the gap somewhere that is then assisting the recombination. So that's why the first heterostructure that was proposed was this heterojunction with this p-type algas front window layer, and then the PEN junction for the gallium arsenide, because here you have the majority of the recombination events, the the creation of electron-hole pair, and is where you really want to prevent surface recombination. Of course, the structures evolved afterwards, for example, by replacing these algas with an even higher bandgap material, for example, aluminum indium phosphide, reducing the thickness of this material down to a few tenths of nanometers, adjusting a little bit the thickness of the emitter and the absorber. Now, I think Alta devices in between 1 and 2 micrometer thick base. And they also introduce a so-called back surface field or a double heterojunction here also on the right side to prevent recombination on the back side of the cell. So this is the record I was mentioning before from Alta. 29.1%, it's over 1 square centimeter in the range of 1 or 2 micron, we don't know actually. And this cell was transferred, so you first grow your crystal or epi layer on a gallium arsenide substrate, and then you manage to remove it from the substrate and replace the substrate with a high reflected back mirror. By doing so, you can, of course, gain a double pass absorption. Stefan will talk about extensively about these problems of light trapping. So we have, in principle, a double pass absorption because this light is reflected at least once. And you can also have photon recycling, meaning, it was mentioned by Uwe, that if you have a relative recombination, you will have a re-emission of photons in all this direction, and some of these re-emitted photons might be light trapped inside the gallium arsenide and reabsorbed once again. And this is not a lossless anymore because it's contributing to increase a little bit the density of photogenerated carrier, and we saw that the splitting of the quasi-Fermi level splitting is linked to the density of photogenerated carrier. So you will increase by this mean the VOC or the open circuit voltage of your cell. Of course, if you limit yourself to one single junction, we've already mentioned these lossless channels, mainly by thermalization, so the photons with a very, very high energy that thermalized at the bandgap edges, releasing phonons, heat, or you have some transmission losses for the photons that have not enough energy to be absorbed because the energy is smaller than the gap. So we already saw this plot, so you already know how to read it. No need to explain it again. This is for a single junction, but if you go with a 3-junction, for example, you can dramatically reduce the losses by thermalization or by transmission, and the higher the number of junctions that you put on top, the lower is these losses. How it works, a multi-junction solar cell, the idea is that you have 3 solar cells with 3 different gaps adapted. The higher bandgap will be here, and will absorb only the blue photons, leaving the green and the red going through for the second and the third. And by doing so, you are basically reducing the thermalization losses. Those are normally connected in series, so it's a 2-terminal device. And in order to make it work, you need to have the same current through the same cell. So we have to calibrate properly the bandgap here and the thickness in order to have the same currents through the same device. This is a very conventional structures for a 3-junction solar cell with the 3 PN junction. They all have the same structures. You have a window layer, so a wide bandgap semiconductor contact, the PN junction made of INGAP with an energy gap of 1.8, and then this back surface field, again in this case, is again aluminum gallium indium phosphide. In order to connect them, you need to use this tunnel junction, and the idea is very simple. The idea is that you are creating electrons and hole for all the cells, and then by using these structures, those are highly doped, for example, gallium arsenide semiconductor here, and by doing so you have some interband transition in between the electrons and the hole, and so they will recombine here, here, and here, and then you have one net current exiting from your 2-terminal device. I think someone else will explain it better, but I would like to mention 15 minutes. I'm going right, okay, I think. I would like to mention a little bit the problem of growing a 3,5 material on a 4,4 material. In this case is the growth of gallium arsenide on germanium. I already mentioned the fact that the lattice contents of gallium arsenide is very close to the one of the germanium. It's about 0.1% difference. And when you grow a material with a slightly different lattice parameter on top of this substrate, for example, you will start with a few layers, and this AP layer will be a little bit stressed because it has to adjust somehow to the slightly different lattice parameters. But it's still a single crystal, perfectly growing, no defects, until you achieve a critical thickness above which the stress inside this AP layer is so big that it has to release it somehow. And the way normally the crystal releases the stress is by creating some dislocation, broken bonds or something like that. And these dislocations are really nasty because they create some states in the gap that then will assist recombination. So this is something we want to avoid. Just to give you an example, those are 3 SEM images of a gallium arsenide or an indium gallium arsenide with 1 and 2% grow on germanium. The stripes are related to these defects. And you can see that if you grow only gallium arsenide on germanium, you have a bunch of defects. If you add 1% indium, it will be perfectly okay. And then again, if you put it too much, it's not okay. The reason why it gets better is because indium is just below the gallium in the periodic table. The atom is slightly bigger, and so by putting 1 atom every 150, you will increase slightly the lattice parameter of this indium, gallium arsenide, and germanium, and you end up with this. There are other problems related to the growth of a 3,5 on 4,4. For example, the fact that gallium arsenide or 3,5 are polar materials, so they have different atoms. And it is not the case for germanium or silicon. So here you have the typical case. You have your wafer. Of course, this wafer is coated with a saw, polished and everything. And if you look at the surface, you will have a bunch of different atomic terraces, right? It's not just one perfectly atomic plane. So you will have this kind of terraces, and you can imagine that if the terrace is composed by just one atomic plane, then when you start to grow your gallium arsenide, most of the time you have some residual arsenic in the chamber, and most of the time you start with arsenic. So you put an atom of arsenic here, here, and here, and then with the gallium, and so on and so forth. But you see that here at this plane, we have a problem because we have arsenic atoms facing a gallium atom. So this is called antiphase disorder, and this is not okay. So this is again introducing defects. What you would like to do, or what you could do, is to have 2 atomic planes like this, so that you can resynchronize the lattice, the crystal of the 3,5. And this is something we can actually do. For example, using germanium substrate that are cut at 6 or in between 4 and 6% off of the 1,100 direction, and from using some additional tricks, annealing and stuff like that, you end up with these double atomic planes terraces, and you can get rid of this problem. But then there are other problems I'm not mentioning today because it's not enough time. So the record 3-junction solar cell, it's owned by Sharp since 2013, for quite some time now, almost 38%, and it's also the record for the under illumination at 300 sun, and the surface area is relatively small. So this is the problem with 3,5, as I mentioned before, is the cost. And indeed, you can, to launch a satellite in space, it's really expensive and has to stay there for quite some time. So we are ready to pay some money if you want to have a big panel or solar cell in space, but it's not the case on Earth. And so what we do instead is to use this concentrating photovoltaic. So the idea is simple. Instead of having a large panel, you have a large optical element such as a Fresnel lens or a big mirror that can focus the light inside a very tiny few millimeter square 3.5 super expensive 3.5 solar cell here. And so by doing so, there are different implementations of this concept, small modules or big thing. You can reduce the price, and you also gain in efficiency, because in this case you have density of photogenetic carrier way higher than at one sun. It depends on the concentration, and by doing so you can increase the VOC, as we saw already. When you have high density of photogenetic carrier, you gain, you increase logarithmically the VOC. There are some drawbacks or problems or things to take care of. First of all, you need direct light, so diffuse light from clouds won't work because your optical element won't focus properly the light. And so the distribution of direct light, it's lower than the conventional global direct plus indirect light, and you normally have these on deserts or whenever you have a clean atmosphere without clouds. So you can't use diffuse light. This is a problem. Then the other problem is that you have to track the sun, because you are concentrating the light, and your optical element will work only if you're directly looking at the sun. So the higher the concentration, the more accurate should be the tracking system, and the higher will be the price of your tracking system. So let's also get hot, and so you have to take care of this. You will have large density of currents, and so you have to take care also of the resistance losses you might have, and you might need to have some frequent cleaning to clean your optical elements. As a matter of fact, there are some installation on Earth or CPV. We had a boom in 2012, 2013, and then it decreased. And it looks like at the moment it's a bit static, the market for CPV. I won't spend much time. I just want to show you here these remarkable results of last year, I believe, with 47.1% for a 6-junction metamorphic. Don't know what metamorphic is, but it's made only by Epitaxial growth, 6-junction at 47.1 by NRL, and the surface is really little. It's 3 by 3 millimeters. So I still have 10 minutes left. I think it's fine. I'd like to talk about a little bit this very hot topic in photovoltaics. The goal is to have a solar cell that exceeds the 30% limit. Silicon alone is very good. We have he owns almost more than 90% of the market, but it's really approaching is the theoretical limit. So we need something else to couple with the silicon. And the question is, what would be the ideal top cell that we can stick on top of a silicon cell to make a tandem, so a multi-junction with 2 junctions, to have more than 30 efficiency, with a relatively low cost, facile integration of silicon, little coupling losses, optical coupling losses between this cell and the silicon cell, and of course sufficient durability. So here you see you have this graph represents the required top cell efficiency to put on top of silicon versus the band gap of this top cell. So if you, for example, if you choose a top cell at 1.7 electron volt and you want to have a tandem at 30%, the top cell should have 20% efficiency. That is what I've written here, right? So 3.5 actually, even in this particular case, they are performing really well. And there are mainly three approaches to do that. So the first one is directly grow the 3.5 on silicon. This is a problem that's been around for, I don't know, 40 years or something. So apart from the problems of polar and non-polar material and so on, we still have a relatively big lattice mismatch, 4% in between, for example, gallium arsenide and silicon. We also have very different thermal expansion coefficient, meaning that when you cool down your cell, maybe it's okay at 500 degrees when you grow it, then you go back to room temperature and it cracks because they have a different thermal expansion coefficient. So this is another problem. But nevertheless, there has been also recent results from Fraunhofer, I believe last year, 24.3% with this configuration, gallium indium phosphide, IGAS and silicon. And this is what I was mentioning before, this metamorphic growth. The idea is that you start with this silicon bottom cell and you start to grow some gallium phosphide. Gallium phosphide is more or less lattice matched with silicon, and then you start to slightly change the stoichiometry of gallium phosphide through gallium arsenide phosphide until you get to gallium arsenide. And this smooth change of lattice constant allows you to grow a very nice gallium arsenide or aluminum iron arsenide solar cell and realize this structure. Of course, it takes some time because you have to grow this layer here, and at the moment the efficiency are not as high, for example, with other approaches. Another possible approach is to grow, instead of grow a 2D layer on top of the silicon, you can grow in the shape of nanowires. And since these nanowires have a very relatively, I don't know, 100, 150 nanometers in diameter, they can relax the stress on the side wall, and so you can grow single crystal, very high quality 3,5 materials or junction on top of the silicon bottom cell. So at the moment, there's nothing fundamentally wrong with this approach. The problem is to have good efficiency, and the moment is still relatively limited. The other two approaches is direct bonding and mechanical stacking. So the idea here is that you first start to grow your top cell. In this case, they use 2 cells. Why not? On the gallium arsenide wafer, you remove it from the gallium arsenide wafer and you bond it on the silicon. And this bond is made basically by activating the 2 surfaces of the 2 wafer in vacuum and then put them together. So this approach allows you to make a 2-terminal tandem. Best efficiency now are 34% by Fraunhofer ISE. The big deal here is that you really have to take care of the interfaces that you are going to bond. They have to be perfectly flat, no dust whatsoever, and it looks like it's not really scalable, this process anymore. And of course, you still have to grow this 3,5 solar cell, remove it from the substrate, and possibly reuse your 3,5 substrate again and again and again to lower a little bit the price. So this is the problem here. The other approach is to go for mechanical stacking. In this case, you have a 4-terminal device, 2 contacts here, 2 contacts here, and there I'll show this 36% efficiency. It looks like not sure if it's true, but 4 terminals apparently is more complicated for modules and is not really envisioned for industry, although it works well. It is not compatible with a texture at the moment, with texture bottom silicon cell. And of course, you still have some light, for example, optical losses in here because you need to contact somehow the 2 cells. So, and again, it's the same problem. You still have to have this epitaxial lift-off, remove this epi layer out of the substrate, and reuse possibly the substrate. I have 3 or 4 minutes. I think I go through this main point here about the epitaxial lift-off and the reuse of substrate. I think this is the big deal with 3.5. If you want to make them cost-effective for terrestrial application, this is the thing you have to do. So the epitaxial lift-off is this method to remove an epi layer of a 3.5 material out of a 3.5 substrate. It was proposed in the 70s, I believe, by Stan and Gonakai, and then improved by Ablonovich. The idea is that you can grow, for example, gallium arsenide substrate, aluminium gallium arsenide, or just aluminium arsenide layer that is lattice matched. We saw it. And then again, your gallium arsenide epi layer, or directly your device, the entire solar cell. And then you rely on the fact that you have, for example, HF solution are selectively etching only the aluminium gallium arsenide, leaving almost untouched the gallium arsenide. And if you apply some stress, you can manage to remove this layer. So this is really timely process. The best I know is based not on aluminium iron arsenide, but on the phosphide materials using HCl instead, which has even a better selectivity. This is the roughness of the substrate after the epitaxial lift-off whenever you use HF, and this is the roughness way lower when you use HCl. Nevertheless, it takes about 8-9 hours to remove the epi layer out of the 2-inch wafer. So it's really slow. There are other possibilities. I list 2. So this is a very old technique, actually, from the 80s. Again, we go back to the origins. For some reason, forgotten. I really don't know why. And the idea is very simple. You get your gallium arsenide substrate, and this time you use a sort of graphite mask with where you drill some holes here, and then you start the epitaxial growth of gallium arsenide. What happens is that the gallium arsenide will, or something that is lattice matched, right, will start to nucleate in the opening here, and then you proceed with Epitaxy that is called lateral epitaxy. Basically, the crystal is sliding on top of this low surface energy graphite mask, and since it's not really touching or only have some van der Waals bonding with the graphite mask, whenever the two crystals join, they will join perfectly. So they demonstrated that you can actually have excellent gallium arsenide films. This is the reference grown on a semi-insulating substrate. You have the mobility here, which is quite good. And then you do the same with this cold cleft process. So before and after the transfer, and the mobility is really very, very similar. Actually, the transfer at this point, you can do it only mechanically, because once again, the 3,5 is stick to the substrate through the opening, but here is basically van der Waals adhesion. So you can manage to remove it mechanically and possibly to reuse the certain number of times. So they demonstrate in this paper quite good efficiency. Those are without anti-reflection coating nor other optimization, using the same substrate 3 times. So I think it's an interesting technology. The other is very more recent, 2 minutes and I'm done. And it's basically coming from this van der Waals epitaxy. This van der Waals epitaxy is normally used for nitrides. The idea is you have your substrate, you put a graphene layer on top of it, and then you start to grow the gallium nitride. So since you only have van der Waals interaction in between the substrate and the crystal you are growing, you might have some nucleation here and there, and then all the atoms that are arriving, they are basically sliding on top of the gallium of the graphene, looking for the first nucleus, and then they start to grow these crystals, and you can get very, very large crystals. Otherwise, if you do that on a simple silicon carbon substrate, you will have nucleation everywhere, and you will have very, very small grains. So what they did recently, a couple of years ago, 3 years ago now, is this remote epitaxy, and the idea now is slightly different. You take this 3,5 substrate, you cover it with one monolayer of graphene, and then you start the epitaxy. And the claim here is that the graphene only partially screens the polar interaction coming from the graphene, and so they can still, the substrate can still direct an epitaxial growth of this layer, because it's a sort of tunneling of information from the substrate. And then once again, since you have a graphene, the real adhesion in between this epi layer and the graphene is only van der Waals, and you can peel it off mechanically. And this is kind of beautiful to me. And this year, like a few days ago, they published another paper that's really, really nice, and you can understand it very well. Instead of using gallium arsenide on gallium arsenide, this time they use gallium arsenide and gallium phosphide. There is almost 4% difference in lattice parameters. So we already saw what happened when you have a difference. The first atomic layer you can manage, is stressed. But then when you increase the thickness and you achieve this critical thickness, then normally what happens is that the epi layer relaxes, creating dislocation. But it does create relocation because it's still bound to the substrate. In this case, probably, instead of creating dislocation, it just loses the epitaxial relationship with the substrate. So you rather stay single crystal, this gallium arsenide on gallium arsenide, than creating dislocation. And this is awesome because you can basically do any material on top of, almost any material on top of any material. The problem here, though, is to have a perfectly homogeneous single layer of graphene on this 4-inch paper. And this is another problem. I don't think it's going to happen very soon. So I'm basically done. And I will be happy to answer your question anytime this week.
We will have some quick questions. Yes.
Sir, how this lattice mismatch affecting the dye structure?
Oh yeah, it's an interesting point. Actually, if your material is stressed, you can actually play with this in order to change different things. For example, you can change a little bit band gap, or you can change the filling of the dopants inside. Or maybe you can increase the mobility sometimes. This is almost used for high mobility HEMT, for high mobility transistor. There's a lot of things that you can play around with this idea to induce voluntary some stress in the epi layer, or maybe use it to compensate and to, yeah, there's a bunch of things to say about that, but yeah, we can talk about later.
And,
Yes?
that graphene you talked about, is it lowering the intrinsic energy also?
Screening. There's another nice paper where they show that they basically measure the surface energy of the substrate using some contact angle measurement, trivially, and they show that whenever they put the graphene, they still have some memory of the real surface energy of the substrate because the graphene only partially screened this information through which is actually nice. It's more convincing because now there are two experiments done in two completely different fields that show that graphene is actually somehow transparent to this polar bonding. Yeah. So it will be a mixture of the surface energy of the graphene plus the surface energy of the substrate to answer your question. Yeah.
Other questions? Can I ask one question
Yes.
to the audience? I have a tricky question.
Yeah, it was
Do you
fast.
think it's a good idea to use this material for liftoff? So the point here was, if you use this material and you etch it, you have a quite rough surface. So it's not excellent if you want to grow high quality.
You have to go through polishing, and again, I didn't mention.
And so this material seems to be much better, but actually the best gallium arsenide solar cells are made with
Aluminium phosphide window layer and back surface
you
field.
remember that the nice thing with free file is that you can grow lattice match materials and ternary alloys, and you can make the heterostructure in one step. And the best window layer to have a selective contact and a passive contact is this material. So the best solar cells use this material for the window layer.
I think you can.
And so
manage.
if you use it for this liftoff, you will etch it.
No, you can always protect the. There's always a workaround. It's not a big deal. Don't listen to it.
Other tricky questions? Okay, you are hungry. It's time to go to the restaurant. Thank you again.